Let's start it.
So, first thing first, let me illustrate our problems. Vibration is undesirable, it wastes energy, and creates unwanted sound or noise. Vibrations can be often caused by imbalance in the rotating parts, uneven friction, the meshing of gear tip, etc. For instance, vibration that is produced by washing machines will normally shake because the laundry weight in the object are out of balance. Hence, we came up with solutions to fix these minor issues. First, we suggest the use of vibration isolation pads to lessen the vibration or shaking during the spinning cycle. One method of reducing vibration is to use dynamic absorbers.
The objective of our project is to analyze the natural frequency and motion for each design. And also we aim to determine the most suitable material and the most suitable design of the isolator pad based on the given parameters. And also we would incorporate modern evaluation tools to verify the theoretical findings. As for our hypothesis, we expect to obtain the lowest natural frequency value and the maximum natural frequency value based on the designs and parameters given for both designs. And also, we predict that the first design with a higher mass and isolators with different stiffness coefficient will be more suitable and efficient. And also, we predict that there will be two different materials to choose from as the most suitable material.
In detailed dimension and parameter subtopic, here is the dimension and parameter that we use to design the new vibration isolator pads.
This is our diagram of the system. Based on our discussion, we agree to assume that the isolator pad will be put at every edges of the machine. Therefore, we need to find all of the value for stiffness of equivalent. Next, so here is the FBD of our system that's showing the action and also the reaction. From the FBD, here we can figure the equation of motion for this system. After that, we can apply all the value of mass and the stiffness equivalent that have been provided from first design and second design inside the equation of motion. From there, we can generate the metric form and find the value for mass inverse and also the stiffness inverse. By using the formula of the iteration method, we can calculate the value for the lowest natural frequency and highest natural frequency. So, here is our result of the calculation.
In this slide, Table 1 shows the comparison between calculation and theoretical method in finding the result, while Table 2 shows the percentage error of different methods that being used. To find a suitable design for the isolator, there are a few factors that need to be considered. The first one is natural frequency. The formula for natural frequency involved with the frequency ratio and forced frequency. From the formula, the natural frequency must be higher than the forced frequency. However, since both designs have higher natural frequency than the forced frequency, hence the frequency ratio is being used as an aspect to choose the best design. It is preferable for the design to have a higher frequency ratio. However, the frequency ratio must be near and not exceed the isolation region. Table 3 shows the frequency ratio for first and second design. Considering the value of frequency ratio for the first design is higher and nearer to the isolation region than the second design, thus the first design is being chosen as an effective vibration isolation. The next factor is stiffness. From the formula of natural frequency, it can be concluded that stiffness affected the value of the natural frequency. Since the value of natural frequency needed in this case is high, thus the value of the stiffness must be small. Table 4 shows the stiffnesses for the first and second design. From the table, it can be analyzed that the total of equivalent stiffness for the first design is less than the second design. Therefore, the first design is more suitable than the second design. Since the design and the stiffness for the isolator has already been decided, hence the Young's modulus can be determined by using the formula. Since the isolator pad is a circular, thus the cross-sectional area and the Young's modulus can be calculated. When stiffness is equal to 280 kN per meter, the Young's modulus is 0.002 GPa, but when the stiffness is equal to 640 kN per meter, the Young's modulus is 0.005 GPa. From the information, the material can be decided by using its Young's modulus from Table 5, which are neoprene and silicone elastomer. Conclusively, considering both factors, the first design is the most suitable and effective for an isolator pad, since its frequency ratio is higher than the second design, and it also has a less total of equivalent stiffness compared to the second design. Based on that, the best material for the isolator with stiffnesses of 280 kN per meter and 640 kN per meter are neoprene and silicone elastomer.
Thank you, doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.